In this video, I'm going to explain the notes which probably you have downloaded from the video description. This video is about velocity and acceleration. And we start with the definition of velocity as rate of change of displacement or change in displacement per unit time. Or you can say velocity is speed in a specified direction. That is, when you get speed and give it a direction, then you will be talking about velocity and not speed. So velocity is a vector. It has both magnitude and direction. From the definition of velocity as a rate of change of displacement or change in displacement per unit time, the symbol for displacement is S. This small triangle here means change, and this one is the time taken for this change in displacement. The direction of the velocity is the same as that of the change in displacement. So when you get the change in displacement, for example, when you have an object moving in this direction like this, maybe it covers a distance of 4 meters to the right, 3 meters this way. The total distance will be 7 meters, but the displacement is this way, which is 5 meters. The displacement is the straight line, is the length of the straight line between the point where it started to the point where it stopped. So I've just used Pythagoras theorem to get the length of the hypotenuse, which is 4 squared plus 3 squared is equals to 5 squared. So this, it will be the displacement, and the direction of the displacement is this way. So if this object takes, for example, 5 seconds to cover 4 meters, and here it may take 10 seconds, now it's moving a little bit slowly, that is T2, then the total time will be 15 seconds. So the velocity will be equal to the change in displacement divided by the change in time, or the time that that displacement has taken to change, which will be 5 meters divided by 15 seconds. And this is like 1/3 seconds, which is 0.333. So this is meters per second. This will be the velocity. If we are asked to give it the direction, we will choose one of these. One of these are the ways in which the direction is given. We can either put an arrow next to the vector. For example, we can just draw an arrow pointing in this direction, and that will be a way of talking about the velocity. We can use the word such as to the right, to the left, upwards, downwards, in which case now this option number 2 does not apply. We can give compass direction. For example, if this one was west, this one is north, we can talk about maybe northwest. That is compass direction. We can give some kind of bearing when we measure that direction clockwise from the north. We can give this angle, or we can even calculate the angle that this vector makes with the horizontal, with the east, or with the west, whatever you have described this line to be. Or you can put signs such as positive and negative. In this case, this one does not apply. Positives would only apply if you are told that the velocity of this object could be 10 meters per second in that direction. When the direction changes and it is moving in the opposite direction of, let us say, 5 meters per second, for example, we can say this is the velocity of the object is negative 5 meters per second. When we don't put the arrow and we just say that the velocity is negative 5 meters per second, it is known that this object is moving right in the opposite direction to the direction which we are taking to be positive. If we are taking movement to the right to be positive, then movement to the left will carry a negative sign. That is, these are the ways in which you can give the direction of a vector. So let's go on. When the direction is not mentioned, it is assumed it is in the positive direction. Like for example, when we just have a number, the velocity is 3 meters per second, and nothing is mentioned, then it is assumed to be in the positive direction. Of course, I've explained a negative sign may signify a decrease in the quantity. This one is something else that you should be able to observe. For example, if you're asked to, let's say the initial kinetic energy of an object could be 5 joules. Let us say the final kinetic energy is 3 joules, and you are asked to calculate the change in kinetic energy. You will get the final kinetic energy, which is 3 joules minus 5 joules, which you're going to get minus 2 joules. The negative in this case shows that the kinetic energy has decreased. So we usually see this kind of happenings a lot. So just be careful about that. Let's look at an example. Suppose we are told that the velocity of an object is 5 meters per second. This means that the displacement of the object increases by 5 meters every second. So for example, after 1 second, we expect the displacement to be 5. After another 1 second, we add 5 onto 5, we get 10. We continue like that until we get a displacement time table, in which case now we can plot this graph here, and we have a displacement time graph. I'm going to talk about the significance of this. Notice that I've not talked about the fact that its initial displacement is 0, in which case expect it to be 0, but of course here I expect that one to be 0, the initial displacement to be 0. So what will the slope of the graph represent? The slope of the graph is going to represent the velocity, because you can see it is change in displacement divided by change in time. And when you look at the definition of velocity, it's change in displacement over change in time. And over here we've got the gradient calculated the same way, change in displacement over change in time. So this one is something that is very fundamental in a displacement time graph. Always understand the slope or the gradient or the steepness of a displacement time graph represents velocity. We are going to see this one in the next exercise. Now, what is the gradient when t is equals to 0? For example, when t is equals to 0, we are going to draw a tangent here, and maybe that tangent will be like that, it will be like this, it will be like this. You can see it gives us this value divided by that value. So you find that when t is equals to 0, the velocity of the object is not 0. The velocity of the object is not 0. It is, for example, here, if I were to work out this quantity, change in displacement divided by change in time, we are going to get 5 meters per second. How is that? This is 25 minus 5, it gives me 20. This is 5 minus 1, it gives me 4. And you can see that gives me 5 meters per second. So even initially, when time is 0, its velocity is 5 meters per second. So let me just clarify this point over here and say that although this object appears to start from some point here, it does not mean that when time is 0, its velocity is 0. It will not be 0. After all, how did it rise all the way from 0 to 5 meters per second within no time? it must have accelerated. So if it was starting from 0, the gradient here will be 0, but the gradient is not 0. So the most difficult question, or the most tricky question the examiner can ask you, is to determine the velocity of the object when t is 0. Remember, if it is just a straight line and there is no curving, then the velocity of this object is the same throughout because it is given by the gradient. So the gradient at this point is 5 meters per second, 5 meters per second, 5 meters per second, and so is at the origin. The gradient is also 5 meters per second. So I would consider this as something that is important, and I'd like you to understand that the gradient when t is equals to 0 is not 0. So the object is not starting from rest. However, we are going to see the displacement time graph for an object which is starting from rest, how it looks like, and it happens in this particular question here, where we are asked, draw a displacement time graph of an object which starts from rest. So here it starts from rest and moves with increasing velocity up to a certain point, then maintains constant velocity, then slows down to rest. So eventually it comes back to rest. We want the gradient initially to be 0, so it's going to be parallel to the t-axis. Then it accelerates, it moves with increasing velocity. So the gradient is going to increase because gradient represents velocity. So the gradient is going to increase. Then it maintains constant speed, in which case now it will be a straight line. And then it slows down to rest. So again, the gradient is going to decrease. And I've already drawn that graph here. And this is it. At this point, you can see if we attempted to draw the gradient, to draw a tangent at this point, you'll find that it will be parallel to the t-axis, which means the value of the gradient of that tangent when t is equals to 0 is also 0. So this shows us that the object starts from rest. So a displacement time graph for an object which is starting from rest will look like this. So it must accelerate. The gradient is going to increase. Over here it is accelerating. And then it moves with the constant velocity. Constant velocity, because the gradient of the line AB is constant. And then over here, the gradient is decreasing. So that shows that the object is decelerating, because if the gradient is decreasing in magnitude, it shows that the velocity is also decreasing in magnitude. And of course here, the velocity is 0 because the gradient is 0. So that is how you would answer such a question. It has been described and then you are supposed to plot a graph, or a graph has been given and you're supposed to describe. Now let's talk about acceleration, because on the same page, I've written notes on the acceleration. Remember, I'm just describing the notes that I've written for you, and these are what you would call short notes, so that they can help you to quickly go through the syllabus. Acceleration, how is it defined? It is defined as change in velocity per unit time. Change in velocity per unit time, or rate of change of velocity. The SI unit of acceleration is, of course, meters per second squared. It is a vector quantity. A vector quantity has got magnitude and direction. What is the direction of this acceleration? How do we get the direction of the acceleration? The direction of the acceleration is the same as that of the change in velocity. I'd like you to underline that, highlight this statement so that you can remember this, because it is going to become very useful when we talk about the concept of momentum and change in momentum, in which case we will need to calculate the change in velocity and state the direction of that change in velocity. So up front, I'd like you to understand the direction of the acceleration is the same as the direction of the change in velocity. As an equation, acceleration is change in velocity divided by the time taken for that change to take place. change in any physical quantity is going to be the final of that physical quantity minus the initial of that physical quantity, of course, divided by time. And final velocity is v, initial velocity is u, and divided by t. So if I can multiply this, both sides, by time times time, I'm going to get v is equals to u plus a t. This equation is referred to as the equation of uniformly accelerated motion. So let's imagine that the acceleration of an object is 4 meters per second squared. What does this mean? This means that the velocity of the object increases by 4 meters per second every second. So if we plot a table of velocity versus time, we're going to have 0, 0 here. After 1 second, the velocity is 4. After another 1 second, it is 8. After adding 4 onto 4, after another 1 second, the velocity is 12. After adding 4 to 8, and so forth. You can see that I'm adding 4, 4, 4, 4. So over here, you can see the object's velocity is increasing uniformly. And so is this graph, because this is exactly what we have transferred here. So a straight line like this shows velocity which is increasing uniformly. Or you can say the acceleration is constant, because the gradient of a velocity time graph actually gives acceleration. And we can be able to prove that, because we would be able to see that the gradient, it will be equal to the change in the quantity that we've put on the y-axis, which is change in velocity, divided by the change on the x-axis, which is a delta t. And you can see this one is in accordance with how we have defined acceleration. You see here, I think we ought to have written that this v minus u is actually change in velocity divided by change in time. We ought to have written something like that. So let's continue. Gradient is change in velocity over change in time, and we can see that this is the same way that we have defined acceleration. So very important, gradient is equals to acceleration. We are going to see that the area under the graph, the whole of this area, for example, if the object reaches that particular point, we are supposed to calculate the whole of this area, which in this case is a triangle. Then the area enclosed by the graph and the graph line and the t-axis, this area here gives the displacement or distance, which is the magnitude of the displacement. Of course, later on we are going to see the difference between those two. Next, I'd like us to look at an exercise. Here we've got a velocity time graph and of a moving object. We are required to describe the motion of the object. Over here, I would say that it's a straight line, the gradient is constant. So the physical quantity which is represented by the gradient is acceleration, and I can say here the object is moving with uniform acceleration or constant acceleration. I can say velocity is increasing uniformly, or I can say the acceleration is constant. Velocity increasing uniformly, or acceleration is uniform or constant. In the section AB, the object is moving with uniform velocity, so its acceleration is 0. And in BC, the object is moving with velocity which is decreasing uniformly, so it is uniform deceleration. Here it is uniform acceleration, 0 acceleration, uniform deceleration, or you can say the velocity is decreasing uniformly. All those are correct ways of describing how that object is moving. Now, when we are asked to calculate the acceleration of the object of course, we know that it applies to this section here. So I'm going to get the change in velocity divided by the time it has taken that velocity to change. And I can see I've got 35 over there, meters per second. 35 minus 0, 3.5 minus 0, and I'm going to get 3.5 seconds. And of course, this one is going to give me 10 meters per second squared. That will be the value of the acceleration. How about the deceleration? I'm supposed to observe that this section gives me the deceleration. So again, I'm going to calculate the acceleration. I will do 0 minus 35 divided by 12 minus 7. And you can see, of course, here I've got negative there. I've got 35 divided by, is it 5? Yeah, it's 5. And I'm going to get negative 7 meters per second squared. That will be the value of the acceleration. In order to answer the question, I will say, therefore, the deceleration, when I call it a deceleration, I just need to write 7 meters per second squared. So it depends on the way this question has been asked. If you're asked to calculate the deceleration, make sure you say what the deceleration is finally. But when you look at our velocity time graphs, we only limit ourselves to talking about acceleration. That is why I started working out the acceleration, because I know I can get it from this graph by getting the gradient. And when the acceleration has got a negative sign, then we refer to it as a deceleration. That is why when I mention the word deceleration, I don't put the negative sign, because the negative sign has been taken care of by mentioning this word, deceleration. Remember that. Of course, a deceleration of 7 meters per second squared means that the velocity is decreasing at 7 meters per second every second. And of course, maybe we can be able to come to this graph here if it was drawn very accurately, and we'll see that in 1 second, maybe the decrease will be 7, from maybe 35 all the way to something like 33 or something like that, somewhere around here, something like that. So far, so good. How about the total distance covered by the object? The total distance covered by the object will be obtained here. The area under the graph will give us the displacement. Of course, when we are calculating the distance, we are actually calculating the magnitude of the displacement. So that S is equal to, that one is a trapezium, but you could work out the area of this triangle plus the area of this rectangle, again plus the area of the next triangle. So, but you can do it once by doing something like this. You're going to say it is a half into, you're now going to call this one to be A, the whole of this to be B, and the whole of this to be H. So A is from 3.5 all the way to 7, and we get 1, 2, 3, 4, 1, 2, 3, 3.5. So you're going to get 3.5 plus 12 times the distance here, this height here, which is 35. You see, I'm using the equation. The area of a trapezium is a half A plus B. I should have written this equation first, times the H, which is this. That is how you would work out that. So I leave you to work out the solution to that. The next question is to try and extract a displacement time graph for the object. This object, which is moving like this. So initially, it's starting with a velocity 0, then it accelerates to some velocity 35 meters per second. So how would we show acceleration on a displacement time graph? So initially the velocity is 0, so it accelerates like that. So after a certain time, which is 3.5 seconds, it maintains constant velocity. So this one will be 3.5, where it's going to maintain constant velocity. That one will be straight. For a certain duration, it is traveling with constant velocity until it reaches 7 seconds. So this is 7. And then from there, its velocity decreases to 0 in a further 5 seconds. So we add 5 seconds in order now we can get 12. And then that's it. It comes to rest at that particular point. So this section here will be straight because it shows that the speed is uniform. After all, gradient of a displacement time graph represents speed or velocity. And over here, that is, I think we have already looked at a graph like this one somewhere before. Yeah, it's right here. Only that this one will just reach this particular point. The description we gave here is the same as the description we are giving to this point. And that is how I would explain those notes. So go right ahead, download the notes. They are given in the video description, and try to go through them the way we have gone through the same. Try to work out the questions the way we have done here. You see the questions that I've shown you how to go about working them out. Now you can practice with the questions. Once you download, just practice with that. And you will understand the notes the way I had meant those notes to serve you.